Okay, so we are talking about Chapter 4, getting started with this set of lecture slides. All right, so this chapter has the sort of general name of Earth, Moon, and Sky. In practice, what we will be talking about are the relative motions of the moon, the earth, and the sun, and the consequences of those relative motions, such as Earth's tilt, the way the tilt remains fixed to the stars and not fixed to the sun, the way the moon orbits around Earth while Earth orbits around the sun, and how the orbit of the moon is slightly tilted relative to the ecliptic plane. These are all the types of things that we will be considering in this chapter. And we're going to start with an idea that we briefly touched on in chapter 2 which is Earth's axial tilt. All right. So to start off, I have a review question for you, which isn't necessarily entirely review, but does get you thinking about the right stuff, which is at which point in Earth's orbit does summer occur? And just to clarify, the review would definitely be the fact that we're talking about an eclipse, um, wrong word, just slipped out, an ellipse. And we see the sun, which is this orange dot here, at one of the two focuses, the foci of the ellipse. And so, some and I guess another thing that we have seen is that, point one would be the perihelion, and point three would be the aphelion. But then this you might not know. At which position in Earth's orbit does summer occur? And by summer, well, think about what that means. What do you mean by summer here? And I just realized I gave away the answer. Yep. So northern one. Yep. So yeah, okay. So at least I got you thinking about it. So at point one, you're saying summer occurs. Are are you saying that summer occurs at point one because we're closer to the sun? Okay. Yeah. So that is actually what we want to avoid thinking because that's not the case. So the answer is closer to what Denise just put in the chat, that summer occurs at point three when we are further, which of course seems counterintuitive, right? Why would summer occur when we're further from the source of heat, right? Well, because we're not that much further, and what really matters is axial tilt, not distance from the sun. So to summarize that in a couple of key statements, our variable distance from the sun is pretty small. One way to remember that is to remember that our orbit is pretty close to a perfect circle, unlike this figure, which shows a not to scale elliptical orbit. Since we're only slightly further from the sun at aphelion than at perihelion, the difference is not significant enough to matter. Therefore, the axial tilt at 23.5 degrees is by far more important. So it's all about axial tilt. And that means that summer occurs in the southern hemisphere at perihelion and in the northern hemisphere at aphelion. Because at those points, either the south of the equator is pointed towards the sun or the north of the equator. And that's exactly what we're going to be talking about in the next few slides, is precisely what that means, how do you understand it in quite a bit of detail. So you don't need to don't have to have that make perfect sense just yet. We're going to be getting into it. Okay. So, which shows the correct rotation axis for the Earth compared to its orbital plane? Well, I'm just going to give you the answer here. It's 2. Okay, so our planet is tilted. By the way, I don't know if 1 and 3 are supposed to be identical. Maybe it's supposed to be rotated. Um, so we've seen a few other typos in these slides, provided by the people that work the textbook. But anyway, regardless, 2 obviously is different than either 1 or 3, and it does show about the right axial tilt. That's that 23.5 degrees, which would be this angle that between the line and the vertical. So between the tilt. So this basically from the number 2 to where that black line runs through the planet, that's our axial tilt. So the Earth, it spins, right? It rotates around the black line, just like a top, but also just like a top, it's tilted, right? So if you get a toy spinning top and you spin it, it does if it starts out perfectly vertical, it won't stay there for long and it's never quite perfect. And so it has a little bit of a tilt, but it's still spinning around its axis. That's like Earth. Okay? So there we have it. Here is a picture showing Earth with its clouds, oceans, and continents. At least you can see Australia. And we are again seeing that 23.5 degrees of axial tilt. Okay? And that's a tilt from, a direction where it'd be in the orbital plane, where the axis would be, exactly perpendicular to the orbital plane, because the orbital plane would be a horizontal line, because the planet is going to rotate, or rather, orbit or revolve around the sun. Okay, so here it is spinning on its axis. See? So if you could like just fix your eyes on Earth and follow it as it moves around the sun, this is what you'd see. Although actually you wouldn't have to follow it for very long because of course this rotation, which I'm kind of going back and forth through, it only takes 24 hours, which is small compared to the time it takes to go all the way around the sun, which of course is, about 365 and a quarter days. Okay, so these next set of figures are going to be crucial for our baseline understanding of why axial tilt leads to seasons. So this is the idea that you need to have in order for everything else to make sense. Okay, so we're going to start by looking at a point where the South Pole is tilted towards the sun. So let's look at that. Okay, so we've chosen a point in the orbit where the South Pole is tilted towards the sun. This figure is showing a elliptical orbit. You can tell because the sun is not quite located at the middle. And so in that regard, this is, again, accurate because it's showing the southern hemisphere, including the South Pole, tilted towards the sun when the Earth is closer to the sun. So this is the perihelion that we're seeing right here, the point of closest approach. So this distance is the perihelion. So perihelion. Be easier if I just wrote the formula, but the one with the eccentricity and the semi major axis. But since we haven't seen that much, I figured we better write the word. Okay, so that's the perihelion. So that's telling us that summer, and you'll see why again if that doesn't make sense, but summer occurs in the southern hemisphere at perihelion. All right, at this point in Earth's orbit around the sun. Okay, so now we've kind of zoomed in on the sunlight and we're looking at how it's hitting the planet at this particular point. All right, so at this point in the orbit, well, if you look, you can see right away that the sunlight, just like, because the sunlight's spreading out as a cone, just because that's what light does. It's a basic property of light. It's actually called the diffraction property of light, that it spreads out to fill in the space. And so the sunlight is doing exactly that. And so when, of course, it's not just one beam, right? It's many beams, but if it applies to one beam, then it applies to the whole thing. Okay, and the sun is distant enough that we don't have to worry about like sunlight coming from the top of the sun or the bottom. It would all look the same. It would all start as parallel. And so even though this picture, kind of shows the sun as being relatively close compared to its size, that's not the case, of course, right? It's just a tiny point of light. But then when the sunlight gets to us, well, we can see that it spreads all the way over the South Pole. Notice how the yellow includes the South Pole, but the yellow does not reach the North Pole. And that's exactly the way light works, right? If this was a ball and I was holding it in front of a flashlight, and you looked at kind of the parts of the ball that were illuminated and those that weren't, it would look like this. Okay, so now we're separating the light by hemisphere. So the orange light is the light in the northern hemisphere, and the remaining yellow light, or the light that remained yellow in color, is the southern hemisphere light. So we see that at this point in the orbit, at this month of the year, we have summer in the southern hemisphere. Summer in the southern hemisphere. And I haven't said this yet, but it's actually a good way to ground these ideas in just like familiar familiar ideas and hard logic, is that this is a particular month of the year. So like perihelion always occurs at the same day, the same, and within the same month. And it's always going to happen around the summer solstice. So that means it's going to happen around June, basically, in a few days, June 21st, right? So this is June, late June in particular, if we're talking about the summer solstice. Okay? So the summer solstice occurs around perihelion. And that's a coincidence. That's not like always going to be true for every orbit. And it's not even true for Earth over the scale of millions of years, because our elliptical orbit actually precesses around. So in a few million years, it's going to be the opposite. We're going to have perihelion at the northern hemisphere's summer, but that's millions of years, right? Over hundreds and thousands of years, it's basically unchanging. All right. But regardless, we're talking about the month of June, summer in the southern hemisphere. Okay. Oh, sorry, wrong month. That would be for the northern hemisphere. Everything I said applies except for this point right here. Southern summer is our winter. So I don't just mix things up. So this would be December. We'll have June soon enough, but there's December. Okay. So moving on. Here it is again. The Earth's axial tilt, just zooming in on the same figure as before. And so that way we can show clearly what's happening here with the sunlight. This little white arc represents the latitudes from the pole that include the Arctic Circle. So the Arctic Circle extends to that last point where the sun is going to be completely covering the pole, right? So it's going to be to how far past the pole the sunlight goes is one edge of the Arctic Circle. And that sort of interesting representation, this, of course, being the Antarctic Circle, because it's the southern, right? I often actually, that's a bad habit I have, sort of failing to identify between the two. I just kind of refer to them collectively as the Arctic circles, but they're not. The northern one is the Arctic Circle, and the southern, southern pole, southern Arctic is not the Arctic, it's the Antarctic. Therefore, it's the Antarctic Circle. But what I was saying about this, seeing the sunlight, and this would be on the longest day of the year for the southern hemisphere, our shortest day of the year in the northern hemisphere, right? So December, late December, around December 21st, there's going to be perpetual sunlight around the South Pole. And that the perpetual sunlight, the sun never setting, is going to apply to the whole section of the Arctic, and it's going to extend to where the sun last kisses the Earth, and that's why we know that the Arctic Circle extends from the pole to where that yellow hits the surface. And then, of course, the surface then curves away and is no longer getting any sunlight. And so anything past the Arctic Circle on the longest day of the year in the southern hemisphere will have an actual, rising and setting of the sun. So if I go a little bit closer to the equator, and I imagine a point right here, and this is just an example to, highlight the concepts we're talking about. So I consider a point, switch to the wrong tool here. So I consider a point right here. So still very far south in terms of a very large latitude and absolute value, maybe, -70 or something. But at that latitude, it's not within the Antarctic Circle. So on this day, the sun will set. But as I move closer to the pole and I get to right this critical point, now the sun never quite sets. And I, dip down, get really close to the horizon, but never set. Because if you think about it, the planet spinning, well, think about it spinning. Well, then this section right here, everything around the pole, is going to spin in a way that the sunlight's always there. You can imagine like there's always going to be sunlight because if you, of course, you're rotating all the way around. You start like here. So let's imagine a point well within the Antarctic Circle, and then you rotate all the way around. Well, then, 12 hours later, you're here. You're still in sunlight. And so you're just going to remain in sunlight throughout that entire day. And so the very edge of the Antarctic Circle has perpetual light for just one day out of the year. This day, if this represents the longest day of the year. And then as we move closer to the pole, we get more and more days of perpetual sunlight around the southern hemisphere summer. And all the same arguments, same logic would apply to the north. Okay. So now looking at the northern pole tilted towards the sun. We've gone 6 months from December. So now we are in June, the northern hemisphere summer. Okay. Happens to be the aphelion, happens to correspond to furthest point from the sun. I only bring that up because it doesn't matter. Maybe like, why do you bring up something that doesn't matter? Just because it's such an easy mistake to make, as we all saw, right? It is so easy to think. It's so intuitive to think, oh, when you're close to the sun, those are hotter days. But as we saw, and as I repeated a few times, that is absolutely not the case. Our distance from the sun just doesn't matter enough. It's all about the tilt. Maybe if our planet wasn't tilted at all, then that small difference would be noticeable, but the tilt dominates, and then the various, ocean currents and all the convection in the atmosphere make it so the only thing that matters is the tilt. There's no noticeable difference from, between aphelion and perihelion. Okay, in other words, southern hemisphere summers aren't hotter than northern hemisphere summers, because you might think they would be because they correspond to, being tilted and perihelion, being tilted towards the sun and perihelion, but they're not. Okay? Neither are northern hemisphere winters colder than southern hemisphere winters on average. But now we're talking about a northern hemisphere summer. So we can use all the same sort of figures like we did for the southern hemisphere summer. Here we got the sunlight corresponding to the tilt when the North Pole is tilted towards the sun. We split the sunlight between the hemispheres, color coding with the orange for the northern hemisphere. And now we notice there's more orange than yellow, which of course was the opposite when we had the South Pole tilted towards the sun. So more light in the northern hemisphere. This means summer in the northern hemisphere. All right, zooming in, looking at the Arctic Circle. As I mentioned before, we can apply all that same logic that I described about what it means to be in the Arctic and what it means, just to clarify in case that wasn't clear, is that the Arctic Circle as well as the Antarctic Circle is defined by that very rule that is the point where you have anything north of those circles, anything closer to the pole, of either circle has at least 1 day of perpetual light and 1 day of perpetual darkness. That's what defines the Arctic and Antarctic circles. Okay? So we've established the rules for summer in both hemispheres, as well as, by relationship, what the winters mean, although we didn't talk about them as much. They are just the opposite. Let's consider two other key points in Earth's orbit, which are when the tilt doesn't matter. Because notice the tilt. I'm just going to highlight something that I haven't yet, which is that if you, and although I've said it many times in the past, I haven't highlighted it just in the last few minutes. Notice that the tilt of the planet, right, the axial tilt, remains fixed relative to distant stars, not relative to the sun. So in other words, if you look at the screen, the tilt of the planet is always towards the left of the screen, because that's the way axial tilts work. For any planet, any orbit, when you have that tilt, it doesn't change throughout the orbit, because that would violate actually the laws of motion, although it's not immediately obvious why. You have to get into a whole bunch of rotational ideas and understand how torque works and angular momentum. But really, it would take a force, a continual force other than the force of gravity, in order for the planet to remain tilted towards the sun. And so that no such force exists, so the tilt is just permanent. All right. So the tilts are almost like these artifacts of how the planets were formed. And since they're just left over, they're independent of the orbit. Okay. And so then seeing that fixed tilt, we see it again, right? The tilt is still towards the edge of the screen, the left edge of the screen. Same angle of tilt. But what's key about this point in the orbit is that now the tilt is neither towards nor away from the sun. And specifically the North Pole, because that's what we're looking at here, is neither tilted away nor towards. Because of course it was tilted away when we were over at perihelion. The North Pole is tilted towards at aphelion, but now it's neither. And if we were to look at the orbit from straight above, we would see that the tilt of the pole is essentially along the path of our orbital direction. So, the planet is moving along its orbit. So it's moving in this direction, the counterclockwise direction. And at this instant, the tilt is in that same, like line of motion. Okay. And when at this another moment in the orbit, when this tilt is neither towards nor away from the sun, is on the opposite side. So 6 months later, now the tilt again is directly parallel to the motion. In this case, that the North Pole is tilted in the direction that the planet is moving. But importantly, it means that there's no change of sunlight between the hemispheres. Now the hemispheres have the same amount of sunlight compared to each other. Okay? And what that would look like, well, if we imagine, here is the Earth, right, with its tilt, and imagine that this picture corresponds to this one where the Earth is behind the sun, and that way, because we're going to color code the sunlight on the northern and southern hemispheres, and so if we imagine this being the surface that's mostly obscured by the sun, then you can imagine the sunlight coming straight from the sun, going kind of back into the image, back into the screen until it hits Earth and does this completely, bathes the planet in sunlight, but not in a way that there's any more sunlight in the north and the south, because the tilt now, right, doesn't change the amount of light. I know this isn't showing the cone, but that's because the cone wouldn't be visible, right? Because the cone is going back into the image. And so we're just showing the equal amount of light between the two hemispheres. All right. And this point in the seasons, in the months, in the orbit, all synonymous terms, this is called the equinox. And of course, there's two of them. There's the spring equinox, which is this one right here, because this is where we're going from. This is the months, between December to June. And of course, the fall or vernal equinox is the one in the back. And so the months that we'd have would be March for the picture in front, and then September for the one in the back. And right around the same, the end of March and the end of September, right around the 20th or the 21st. Right, so the two equinoxes. All right. So 6 minutes ago, Maria said she was having trouble with the connection. Let me know if that's widespread. Hopefully the recording quality is good. Just went to go check the chat. Make sure there wasn't any other questions that have popped up. Let's see. All right. Okay, cool. Good to know. All right. It's looking better, apparently. There we go. All right. So we've got a few minutes. We'll continue on with this. All right. So at this point, the slides have taken a pretty general approach to explaining the difference between the seasons, which is a great place to start. And what I mean by that is that our main argument has been that there's more light, right? You just say, look at this cone of light. There's more light in the northern hemisphere than the southern hemisphere. And at the equinoxes, it's equal. That's obviously not a very exact explanation. It's a good start, but it would be open for challenge, in a scientific community. You'd want to have a more detailed, a more analytical approach. And obviously, that can go really heavy, but we're not going to do that. But we are going to go a little bit more into a justification, a more detailed explanation of what it means to have more light. And to do that, we want to talk about the sun angle. Okay? So let's imagine Eugene, Oregon, right? Not an imaginary place, but let's imagine ourselves there. Okay, we're at 44 degrees north, so we're in the northern hemisphere, and we're going to imagine what the sunlight looks like at that latitude at different points in the year. Okay, so let's have, first of all, an Earth that isn't quite Earth. So this is alternate universe Eugene, Oregon so far. And why is that? Well, because the Earth is not tilted. So far, the Earth that we're showing in our figure here has no axial tilt, and the sunlight is coming straight in. Now, that may be because, you know, this is like the equinox, but even then, it wouldn't look like this because then there still would be a tilt, but the sunlight would be coming from, you know, like outside of the image. So we'd have to kind of show it in some weird 3D way where the light's kind of, approaching from the bottom, so to speak, right? But actually representing coming from the front, so far it just doesn't work. Doesn't actually match Earth. So let's give it its appropriate tilt. And to start with, we'll consider the northern summer. So we've tilted the North Pole towards the incoming sunlight, in other words, towards the sun. Okay, so corresponding to sometime in June. So the sunlight's going to come in. The sunlight comes in as just straight in parallel rays. So if we think of this, the light, it would approach as just a wall of light. And that, again, that's because the sun is so far away. All right, we're now going to consider a couple of angles. First of all, the horizontal yellow line is just the incoming light. The dashed black line represents a line that is perpendicular to the surface at that point. So it's just a line that points towards the zenith of an observer in Eugene, Oregon. Remember those local sky terms? That's what this is. So the dashed line will be pointing towards the zenith, just any point straight overhead. And then we're going to consider the angle between the incoming sunlight and the zenith. Okay? And that is 21 degrees. Okay? 21 degrees. And where did we come up with that number? Okay? So let's see I remember. Yeah, okay. So we'll explain it here. So I'll mention a little bit, but I won't write the equation since we're going to see a version of it in a moment. Is that it comes from considering the latitude, which we saw here, 44, and the axial tilt of 23. Okay, and a little bit of 23.5, but then if we do some rounding, that's where the 21 comes from. Okay, it comes from considering both the latitude and the axial tilt. All right, but if you're wondering exactly how, I'll show you in a minute. Okay, so let's then consider our summer solstice in Eugene, Oregon. Okay, we're going to imagine a couple of dogs, basking in the sunlight. What kind of light are they going to be able to warm themselves up in? All right. Well, it won't be directly overhead, right? So if the sunlight was, coming from exactly the zenith, the dogs would have to be at a different latitude because the sunlight will never be directly overhead in Eugene, Oregon. We can tell because we're visualizing essentially the longest day of the year, the most direct sunlight we're ever going to have. And it's not, the yellow line is not overlapping with the zenith direction. So there is never a day of the year in Eugene, Oregon, or many northern latitudes where the sunlight comes from directly overhead. In fact, you have to be in the tropics to have a day of the year where the sunlight comes from directly overhead. That's what defines the Tropic of Cancer and the Tropic of Capricorn. They are latitudes where there's at least one day of the year where the sunlight is directly overhead. All right. So that's just like, a very similar definition to the Arctic and Antarctic, where you have, at least one day of the year where there's perpetual light or perpetual darkness. But since we're not in the tropics in Oregon, we have overhead sunlight, but not directly. The angle between the sunlight and the horizontal is 69 degrees. So first math I want to show you, and which is one of the last topics we're going to cover before we wrap up in about 2 minutes, is this 69 and how it relates to the 21. Well, it might be obvious, and it's going to be simple to explain. They simply sum to 90. Okay? So when we talk about the angle of the sunlight relative to the vertical, which is another word for the zenith direction, well, that's 21. Great. Well, here in this figure, they're showing the sunlight coming in relative to the ground, to a line that points to the horizon. Well, the difference between the zenith and the horizon is 90. So that means that this angle right here is the 21 degrees. And 90 minus 21 is 69. Okay, so that's how we can talk about these two angles, direct relationship between them. Okay, so now this angle, the 69, is called the altitude. That is the official local sky term for locating any object in your sky relative to the horizon. The other one, which we briefly touched on, is called the azimuth, which is measured relative to the western direction. Yeah, due west. But we don't care about that right now. So anyway, the sun's altitude is found by taking 90 degrees minus the latitude plus the axial tilt. And which altitude? The sun's altitude at the longest day of the year, at the day where the sun is as high in the sky as it will ever get, the summer solstice. Okay? So the northern hemisphere summer solstice, this is the equation you would use. All right? It would be really similar for the southern hemisphere, but you would have to consider that the latitude is defined as negative, but the ideas would be real similar. But we're only going to show the northern hemisphere in the slides. Okay, so just to point out as the last thing for our class today, 90 degrees minus the latitude, which was 41 degrees. All right, so 90 minus 41 is going to give us 39. All right, then 39, was it 41? Doesn't sound right. 44. There we go. So 90 minus 44 is going to give us our 36, okay? And then 36 plus 23.5, okay? And then we round, that gives us 69. That's where it comes from. So 90, let's write it real fast. 90 minus 43 plus, okay, plus then 20, yeah, plus 23. Okay, that's gonna approximately give us, I know the rounding, trying to hurry. I don't want to double check my work, but there we go. Approximately gives us 69. That's where you get the value. Sun will never be higher at that latitude. Okay, all right, that wraps it up for today. We'll continue to talk about chapter 4 tomorrow.
Thank you.
Thank you.